turn our attention to our first topic, which is simple harmonic motion. So, simple harmonic motion refers to objects that are undergoing a repetitive motion, like a pendulum swinging back and forth, or a spring bobbing up and down, or even something undergoing circular motion. All of these things are vibrating with some repeated oscillation. And we're first going to talk about an example using a spring. So imagine that you have a spring bobbing up and down. So imagine the spring is at rest. This is going to be the equilibrium point, where x is 0. And we're going to compress it to a maximum height. That'll be the amplitude that it has. And we're going to let go of it, and it's going to start bobbing. And it's going to bob, it's going to go to equilibrium, and then it's going to go down exactly the same height that it went up, that we compressed it. So if I compressed it 5 centimeters, it's going to stretch out 5 centimeters below equilibrium. We'll go through equilibrium again. So this is equilibrium, equilibrium. And we usually call these the maximum displacements, the maximum displacement. So we have maximum displacement, and we have the equilibrium point. And if we were to graph that, okay, so it starts at 0, okay, and then it gets pulled up. Actually, it's not starting at 0. What we're going to do is, when it's hanging at equilibrium, we're going to compress it to some high point. So it's going to start here at its maximum point, and then its maximum displacement is going to go to equilibrium. So this is x and this is t. It's going to go to its bottommost point, equilibrium. You notice that this is not going to be a linear graph. So remember that if a position graph is linear, that represents that the object is undergoing constant velocity. If it's a quadratic graph, it's undergoing constant acceleration. So it's changing its speed by the same amount every instant in time. This is neither one of those because it does not have constant acceleration, but it is accelerating, okay? It is accelerating, but it's not constant. And that's because the force acting on it is not constant. It changes. So think about if you have a rubber band. It gets harder and harder to stretch it, right? Same thing with a spring. So with oscillators, the force that's causing the oscillator to try to return to normal, it changes with displacement from the equilibrium point. So when it's at its most furthest points, its maximum displacements, it has the greatest force acting on it. And when it's at equilibrium, it has the least force acting on it. And that means that it has more acceleration at the maximum displacements, and it is traveling the fastest at the equilibrium points as it goes through the equal points. So that force that is doing that, that's directly related to the stretch of the spring, is called the restoring force. And that's described by Hooke's law. And it says that the force of the spring on the object that's oscillating up and down is in the opposite direction. So if I put a mass on here, it has a certain weight, right? Weight is mass times gravity. And the spring is pulling back equal and opposite to it. And so it's in a negative direction. That's what negative is. It's equal to the stiffness of the spring constant, which is in newtons per meter, times how far you've stretched it. So let's say that you have a mass of 10 newtons and you stretch it 5 centimeters. What's the spring constant? Well, the mass is 10 newtons. So we put 10 newtons on it and it stretches 5 centimeters. So the force that's causing it to stretch is 10 newtons. And 5 centimeters is 0.05 meters. So everything needs to be in meters and seconds. So K is going to be equal to 10 divided by 0.05 newtons per meter. So if we do that, we get a spring constant of 200 newtons per meter. So it takes 200 newtons to stretch it or compress it 1 whole meter. At maximum displacement, it has the maximum, it has, oops, my bad there. At maximum displacement, it has 0 velocity. It actually comes to a stop, and it's changing direction. So it has the greatest acceleration at maximum displacement. But at equilibrium, it reaches its max velocity. So that means that it has the maximum amount of potential energy at its maximum points, and it has its maximum velocity or maximum kinetic energy when it reaches equilibrium. So it's going to go back and forth, but it's conserving it, right? So if it had 100 joules of kinetic energy at its equilibrium, it's going to have 100 joules of potential energy, because these are simple, which means that they have no friction in the systems. So once again, the total energy is going to stay the same, right? It's going to, if there's no friction in the system, if there's 2 joules of kinetic energy at the equilibrium point, that's going to be converted into 2 joules of potential energy at the maximum displacement points. Now, let's talk about how we describe that. We already said that the graph would be some kind of sinusoidal graph, and it turns out that it is. The generic formula for the position of something that's oscillating on a spring is the amplitude times cosine of something called omega t plus v. So let's talk about this. Well, first of all, let's just talk about this object bobbing up and down. When the object bobs up and down, when it makes, so let's say we compress it to its highest point, and it goes through equilibrium, goes down to the slowest point, and then it goes through equilibrium, and it comes right back. That is one oscillation. The time for that is called the period. It's measured in seconds. So it looks like it goes from 0.5 to 2.5 seconds, so it takes 2 seconds. So T, for this example, is 2 seconds. The frequency is how many oscillations per second. So this is 2 seconds per oscillation. The frequency is 1 over that, right? It would be 1 over 2 or 0.5 oscillations per second. We have a name for that. It's called hertz. So it has a frequency of 0.5 hertz. But if I want to know where the mass is at any point, like at 1 second or 2 seconds or 1.2 seconds, and this is a cosine function, I need to be able to locate where cosine is on a circle, right? Because we take cosine of angles, and frequencies and periods aren't going to give us that. So we have something called the angular frequency, where we convert frequency into, an angular radians per second value. So just remember that when you make one oscillation around a circle, one oscillation is equal to 2 pi radian. So if I want to know how many radians per second, I can convert 0.5 oscillations per second to radians by converting one oscillation to 2 pi radians, and that's going to give me 0.5 times 2 pi, and that's going to give me units of radians per second. So the formula for angular frequency which is omega, is 2 pi times f. So if your f is in hertz, if you multiply it by 2 times pi, then your omega would be in radians per second. So in this case, omega is going to be 0.5 times 2, which is 1, and pi radians per second. Now, we can write our generic formula here. Now, the other thing I'm going to tell you is that this number here is called phi, and it's a phase shift. So remember when I first drew what this graph would look like back here? And I said it would look like a cosine graph, right? But if you look at the example given to you right now, it looks like a sine graph. It's because it didn't start. We didn't start taking data when it was at its maximum highest point. We started taking data when it was at its lowest, at its midpoint, this equilibrium point. So this is shifted a certain number of radians. For right now, we're not going to worry about that unless I tell you what it is. But for this, the amplitude is how high the wave is from the equilibrium point. So if equilibrium is at 0, it looks like this is oscillating between 1 and negative. So the amplitude is, and this is in meters, 1 meter cosine of pi radians per second times time. And that describes that function that we just had. Okay, so that is the cosine function that describes this. So when we look at this, if I know what A is and I know what omega is, then I can write that equation. And also, if I give you an equation, then you can pick out information about that oscillator. So for example, we have a 50 kilogram mass and it's hanging on a spring, and the function that describes it is 2 centimeters times cosine of 2 pi t. So remember, the generic is x equals a cosine of omega t. So that means that a is 2 centimeters and omega is 2 pi. So I already know that the amplitude is 2 centimeters, or 0.0200 meters, and that omega is 2 pi radians per second. So from omega, I can find f, right? I know that omega is 2 pi f. So f is omega divided by 2 pi, or 2 pi radians per second divided by 2 pi, which is going to be 1.00 hertz. The radians, this is understood to be radians here, it's going to cancel out. And my period is going to be 1 over that, which is going to be 1 over 1 hertz, or 1.00 seconds. So I can just take this formula and I can figure out all that information very simply. All right, I can also be given information and write that generic equation. So an oscillation spring is stretched 5 centimeters. So that's what A is. So A is 5 centimeters, or 0.05 meters. And it's released. And it makes 10 oscillations every second. So 10 oscillations every second. Every 1 second. That's going to be my frequency, right? Because frequency is oscillations per second. So it is 10 hertz. Omega is going to be 2 pi times that, which is going to be 20 pi radians per second. And if I want to know the period is the inverse of that. So 1 over 10 hertz is going to give me 0.100 seconds. So if I want to write my position function, which is A, or 0.05 meters, times cosine of 20 pi radians per second times t. And we'll just assume that it's starting as a perfect cosine. We're not going to worry about phi right now. Now, there's also a relationship between the angular frequency, or the frequency of it, and how stiff the spring is and how much mass the spring is. So it turns out that omega squared equals K all over M. So if omega, and let's go back to that problem, is 20 pi radians per second, I can actually figure out how stiff that spring is as long as I know what the mass is on it. So let's go back to this one. I want to know what the spring constant is. Well, the spring constant is related to omega squared equals K over M. K is going to be equal to omega squared all over M, which is going to be, omega is 2 pi radians per second squared divided by, and I have to make sure that's in kilograms, 50 kilograms. So now I need to do this. So 2 times pi, let's clear this, 2 times pi times 2 times pi equals, so that's the square of it, divided by 50. I'm getting, let's just double check that again, was 0.789 or 0.790 newtons per meter. Pretty easy. Our next lecture will focus on pendulas.